Hmm. This is a difficult one. Okay. Sure. Let's begin. This is a difficult topic, by the way. I will always be honest when I know that things are difficult, especially if you've just done this for the first time. It will not have been straightforward. So yeah, I'm happy to help. Um, I will get to that booklet three question as quickly as possible. Okay. So question one, two, five from this one. Some of these will overlap. Okay, so just keep an eye out because there will be some things that are the same in all of them. Right. Question one says crude oil is a mixture of hydrocarbons. I will try and explain things as I go. Um, but oh, oh, right. Just so you know, in case you get this question, a hydrocarbon is a compound that contains hydrogen and carbon only. For example, this CH4 or this C2H6 or any number of them, but the numbers just change, but there's only C's and H's. A lot of hydrocarbons are found inside the crude oil, which is the stuff that we get out of the ground. It is one of the three fossil fuels. And the answer to this question is that it's the remains of plankton. Fossil fuels generally are the remain. We say they're the remains of dead plants and animals buried underground over millions of years. But crude oil specifically comes from this, which is a sea organism. And therefore, we find a lot of oil under the sea because it's this stuff that has died and been buried underground. And underground is the same as under mud. So that's the answer. Right. Right, this stuff, when we get out of the ground, has to be separated out because it's got short hydrocarbons and really long ones as well. So we want the short ones out, we want the long ones out separated. We do this thing called fractional distillation. Simply put, what we do is we heat up all of the oil first so that it all evaporates. Later, we cool it down and it starts to condense, but it condenses at different temperatures because they've all got different boiling points. And so we're able to do this thing where we separate them out and they all condense in different places. So C would be the answer there. This is booklet one. It is indeed booklet one, I believe. Yeah, because that's two and that's three. Yes, it is one. Um, so if you have any other questions, I'm going, I want to do question two to six because I'm going to do a lot of them because it's quite a difficult topic. The name of that entire process is called fractional distillation. This question should not be too difficult, but it just involves counting. So when we draw these pictures of these bonds, it often looks a bit like this. Now, this is the same thing, but it's like a three-dimensional picture of it. So what you're meant to realize is that these three in the middle are the three carbons. So there's three of those. And then the white ones are the H's around the outside. One, two, three, four, five, six, seven, eight. Just counting. And all of these things in the middle are that's joining them together is a covalent bond. A covalent bond is when you have these electrons being shared and you have these like overlapping circles in the diagrams that we do. So that is the answer to that. And then the general formula for alkanes. There are two types of hydrocarbon. There's alkanes and alkenes with an E. Alkanes all have this formula where the number here gets doubled and add two to get to the number of H's. If I double three and add two, what do I get? I get eight. If I had four, then I double it and add two, and I'd have 10 of those. But with alkenes, the formula is that whatever this is, you just double it to get to that. So when it says the general formula for alkanes, it's referring to this. This is a long-winded formula way of saying that whatever this number is, we double it and add 2 to get to the number of H's. So if it was C 100, to get to the number of H's, we would double 100, 200, and add 2, 202. That is the general formula for alkanes. This is the general formula for alkenes. That isn't something you need to know. Okay, that was one. And then this one, I mean, I shouldn't need to answer this really. If I said that we use 8 billion plastic bags and then the next year we only use 1.3 billion, and the question is, what's the decrease? Don't you just do 8 take away 1.3 billion? That's it. Just the difference between the two. Um, then the next question. Um, I'll just do most of these, I think. Yeah. Yes. So cracking involves, so if I have like a really long hydrocarbon, if I just make this long and long and long and long, long, really long, and there's H's around, that's really long. Okay. These long ones are not as useful to you and me because they don't burn as easily. What we like to do is burn things because then we get cooking, fire, and heating, and petrol and stuff for our cars. But that only uses these shorter ones. So there's something we can do if we have a long one. We can do something called cracking, where we kind of break it into smaller ones, and so the smaller ones are more useful to us. The conditions for cracking are always high temperature and a catalyst. There is nothing more you need to know. If you hear the word cracking ever again, just think high temperature and a catalyst. So make it really hot and use a catalyst. A catalyst is something you add to a reaction to speed it up, and it changes to become something smaller. Right. Then it says draw butane, which is C4H10. So it's already drawn a bit of it for you, but we know that we need four of these C's. So I'm going to put the other two C's there because they always go in the middle. And around the outside, we need to fill it with H's. So put a H there, put a H there, put a H there, put a H there, put a H there. The way to do these diagrams is to make sure that every carbon C that you look at should have four lines coming out of it. One, two, three, four for that one. Then one, two, three, four for this one. One, two, three, four for that one. And then one, two, three, four for that one. They've all got four lines coming out. That represents the four things they can join with. And every H can only join with one. So there's only one line coming out of every H. Butane burns in oxygen. Complete the word equation for the complete combustion. Whenever we burn something, we react it with oxygen, and the two products are carbon dioxide, which can go into the air and do bad things, and water. That is the formula for combustion, the equation for combustion. The test for alkenes. I'm going to do this question once because I think it gets repeated quite a lot. If I gave you a test tube and I said, one of these is an alkane, one of these is an alkene, which is which? How would you know? There is a test that you can do. The test involves adding them to bromine water. Bromine water is orange. Let's get an orange. Orange. Okay. And if it mixes with an alkene, it changes from orange to colorless. The reason for that is that alkenes have the ability to react with it, but alkanes don't. So with an alkane, it wouldn't change color, it would stay orange, but with an alkene, it changes color. And that's because alkenes can react with things. This is just an answer. The answer is sustainable development. Sustainable development is when you do something today that might not benefit you, but it will benefit people that are alive much further in the future. For example, planting trees is a sustainable thing to do. It might not benefit you much today or even in your whole life, but if there's lots of more trees, then it will benefit people in the future because there will be hopefully less global warming and other things. Question three. Crude oil is a mixture of different substances. That's what it is. And all of the different substances, by different substances, we mean we have some really short hydrocarbons like that, and some really long hydrocarbons and everything in between. So short and long. The difference between these short and long things is that they all have different boiling points, and that is what allows us to separate them in that process called fractional distillation. Oh, that's the answer to the next question. Distillation, fractional distillation. Okay, petrol is one of the fractions from crude oil. This shows some of the gases produced. What type of reaction happens to petrol? Petrol is burnt in a car engine, and the proper chemical name for burning is combustion. This is the same as the question that was earlier, where we had to complete the equation. When you burn something, you add oxygen to it. Well, it tells you there, really, so you should get that bit anyway, with oxygen. The two products of burning are usually carbon dioxide and water. Um, why should sulfur be removed? It's a difficult question. You wouldn't know this yet. Why should sulfur be removed from petrol? Because when you have sulfur inside petrol and when you burn it, it can become something called sulfur dioxide, which can cause something called acid rain. Acid rain is when the rain that comes out of the sky is slightly acidic and it affects plants and stuff. Um, Propane, why is it useful? It's a fuel. All of these things that end with anes are fuels. That's what we're doing here. We're trying to get a fuel. A fuel is something that burns. That's what we're trying to do here. And complete the formula for ethene. If it's an ene, it has a double bond in the middle. For one of the carbons, there's only two carbons here, so two of them have a double bond in between. So you put that in, and that is the answer. Um, I've already answered that question, kind of. I explained what happens to bromine water when it reacts with an alkene earlier. Um, and then this answer, again, you might not have got to it in the lesson, but the answer is a polymer. When you join lots of alkenes together, in fact, no, that won't be the answer. The answer must be polypentene. Let me check what the answer says. Yeah, you can say polymer or poly, but polymer is fine. Okay, question four. I'm not going to answer that. I think you should be okay with that. Same with that. Question part B. Here, butane is out of these, the only answer that makes sense is a compound. A compound is two or more things joined together. It contains carbon and, I'll let you guess because it's fairly obvious. Each line represents a chemical bond. Okay. Um, got Mark wondering if we're going to go through the science topic in person on Sunday. On Sunday, and this week, we are doing some physics revision. So therefore, if you have some specific physics topic in your science test, then you can ask him about those. But we are doing some physics generally revision on energy and stuff like that, I think, this weekend. Um, Formula for butane. Butane is the one that contains four carbons. If it's an ane, then what you do is you double this number and add two, and you get to 10. And that's why the answer is that. Um, I won't do that. Um, okay, well, this question. Coal burns in oxygen and produces all of these different things. Name an element that's in coal. All you need to do is pick one of these letters and name the element. So you could say carbon. You could say sulfur. You could say hydrogen. You can't say oxygen because that's the thing it's reacting with. So carbon would be enough. Um, it's quite a difficult question. Hydrogen can be made from fossil fuels. It burns rapidly enough to produce water only. Um, so what this question is to give you a little bit of a background to this question briefly. For e-booklet 3, I shall get to that, don't worry. So the advantages of using hydrogen as a fuel. What you're meant to know here is that fossil fuels like coal and oil produce these harmful gases when we burn them, like carbon dioxide. They've told you in the question that hydrogen only produces water. So isn't that an advantage of using hydrogen, that there's no carbon dioxide produced? Because that is one of the things that causes global warming. Um, and what else could we say here? Well, the other answer is that it burns very quickly. So it tells you in the question it burns very quickly. So really the answer in the question. That's enough. Um, I won't answer that one. That should be quite easy. General formula for alkanes. We saw this earlier, but I've mentioned it a few times. It's this thing of doubling and adding two. Um, Booklet 3Q5. Okay, I'll put in 5D. Yes, fine. Um, Describe and explain how crude oil is separated into fractions by fraction distillation. This is the hardest question here, but you should have had something in your notes that basically told you what you needed to say here. So I'm going to simplify this. The first thing we do is we heat the crude oil really hot until it vaporizes. That means it all turns into a gas. Then what we do is say we put it into this column, and as it goes up, it cools down. It's hot at the bottom, it's cooler at the top. And then it's made up of lots of different things, all of which have different temperatures at which they turn back into a liquid. So one of them turns back into a liquid here, and we have these trays ready to take it off. The rest of it carries on going up. Then some of it cools and comes off. The rest of it keeps going up. Some of it cools and comes off. So we are able to separate this because they've got different boiling points. So I want to say the different fractions, it's called fractional distillation, the different fractions, have different boiling points. This might be the answer, by the way, to some of the other questions that you guys are asking me. If it says, explain the process of fractional distillation, this is the answer, so I won't repeat it. So it's quite complicated, but the idea is that as it goes up, it gets cooler, and as a gas gets cooler, it eventually turns into a liquid. And so some of the gases will turn into a liquid lower down, and some of them will do it higher up, and then we can separate them by doing that. Just check what other things have been said. Okay. Um, just bear in mind that, I mean, I appreciate somebody's just asked me lots of questions here, but if any of them are repeated in what I've already done, then I won't answer them, just so you know, and I think they will be. Complete the equation for this reaction. This is, again, not easy to do, but I shall tell you how you balance equations. Um, you're meant to know that we're going to end up with more C's and H's. If you've only got C's and H's to begin with, you can only finish with C's and H's. But then you have to do some counting. On this side, we've got 12 C's and 26 H's. Let's focus on the 12 C's. We've got 12 C's on this side, which means we can only have 12 C's on the other side. How many C's have we got so far? That big two doubles these two, so there's four of those. So we've got four of them out of 12 of them. How many is left? Eight. So we need eight there. This big 2 also doubles these 4 H's, so there's 8 H's. How many do we need? 26. So 26 take away 8 is 18. So we must have 18 of those there. Difficult question, though, so don't worry. Give two conditions needed for cracking. The answer is always the same. High temperature and a catalyst. They're the two things that you always need for cracking. I've done the whole thing. Done the whole thing. Right, let's move on. Booklet 3. Let's see what we've got here. So we'll do these in order. 4C, what you mentioned? Right, 4C is a difficult question. Well, it's not difficult, it's just long, right? That's why you're asking me. So it says, compare the structure and properties of methane and hexane. Right, we've got this thing called methane, we've got this thing called hexane, okay? It's drawn them out for you, which is a clue as to what you need to say. It's also told you the melting and boiling points of methane and the melting and boiling points of hexane. You should be able to look at these numbers and realize that one is bigger than the other. This number is bigger than this number because it's less negative. This number is bigger than this number. So you can say that hexane has a higher melting point and boiling point. That's probably 2 marks because you mentioned two separate points there about their properties. Then you can also say, get some really easy marks for saying that methane has got one carbon atom joined with four hydrogen atoms. However, hexane, what does this have? Hexane has got six carbon atoms joined with, if you count them all, there's 14 hydrogen atoms. I'm just simplifying the answer. Okay, so sometimes you can not state the obvious in these things. You can just look at it and be like, well, that seems strange, but it is there. Um, so that's that. So you can just get marks for saying that. Remember, when you do compare questions, think of the word compare as meaning tell me the differences between these two, but also the similarities. Sometimes we forget that compare can mean things that are the same. I think we naturally do differences. Think of that for English exams as well. You have to compare two things, and sometimes you naturally go towards what's different. But compare can mean what's the similar as well. Both of these two things are what we call hydrocarbons because they are made up of carbon and hydrogen only. There's different amounts of them, but they are still hydrocarbons. That's a similarity. And then I'm going to put one more difference. The shorter ones of these things, okay, we prefer the shorter ones because they burn better. Um, and the word for burning is flammable. So methane is more flammable as well, I'm going to put. And I think that should be enough to get most of the marks there. Okay. That is question 3 for C. Question 4E as well. No, you said something else, didn't you? 5D. The test for hydrogen. Yes, this is not something we covered, but if you have a test tube, and you may have done this experiment depending on whether you've done this yet or not, but you will very soon if you haven't. If I have a test tube that's got some hydrogen in it, and I want to prove to you that there is hydrogen in it, what I could do is get a splint, which is a piece of wood, light it. Okay. If I put that near this gas, do you know what will happen? I will hear a pop sound. That will prove that it's hydrogen because hydrogen burns with this squeaky pop. So the test is use a lit splint, and the result is you would hear a squeaky pop. Squeaky and pop, both examples of alliteration. If you want to just divulge into some English. Um, did I do 4C? No, I didn't do 4C. Oh, I did do 4C. Okay, 4C is done. Um, Does it make a pop? Capital letters. Yes, it does. And here a squeaky pop. Um, right. Okay. Let me see what other questions. So there's only that's everybody's question apart from that big long list of questions. So let me see what we've got here. So I've already answered this question earlier, but I will just tell you again. The conditions for cracking are high temperature and a catalyst. That's what you need to know. Um, The test for alkenes is always the same. Like I said, I shouldn't really tell you this, 'cause I've said it already. The test for any alkene is you use something called bromine water. And if it's an alkene, the bromine water changes from orange to colorless. A chemical reaction takes place with an alkene only. If it was an alkane, it doesn't change color. 6B, sorry. Let me look at that first. Did I not do that? I thought I did that. 6B. The answer to this question, again, you might not have got to this in the lesson, but basically, if I just give you a little bit of indication here, alkenes, so this is an alkane, it's called ethane. This is an alkene. Sorry, there's more to it. The difference between, what am I doing? The difference between an alkane and an alkene in terms of as you look at one of these diagrams is alkenes have this double bond. So they have this one double bond. The advantage of having this double bond is that it has the ability to open up and join with other stuff. Okay. Alkanes can't do that because they don't have that double. So the double can become a single and join with other things. An example of what it can do is make something called a polymer. Polymer is when they join with each other. Lots and lots of them join with each other. Poly means lots of, which is why a polygon has lots of sides. Um, so polymer means lots of these things joined together. But those things have to be alkenes. They can't be alkanes because alkanes don't have that double bond. So the answer to that question is alkenes. Um, that's it for those. Right, let me go back to the others. Two, C, two, D. I've already answered this question. Three, again, I'm not going to answer B. B. I mean, I've already answered this in the previous one. It was the same question. We said butane is a compound. Um, these things are hydrocarbons, which means they only contain carbon and hydrogen. And the little lines here between them are chemical bonds, specifically a covalent bond. Okay. Um, and then you also asked me for 3B, 4AB, 4C. Um, Crude oil is formed by the decomposition of something called plankton. Plankton is a sea organism which dies and becomes crude oil. The name of the alkane that has three carbon atoms, I'll be very surprised if this is not in your notes, but I'll tell you anyway. If it's got three carbon atoms, we call that propane. The order is if there's one carbon, it's called methane. If there's two, it's called ethane. If there's three, it's called propane. If there's four, it's called butane. And after that, five, six, seven follow the shapes. So it's like pentane, like a pentagon, or hexane for a hexagon, and so on. But annoyingly, just learn the first four. I have done that question for AB. For C, I did earlier. Test for alkenes we've done now several times. And 5B, the test for carbon dioxide I will finish with. The test for carbon dioxide is that if you get some stuff called lime water, which is a colorless solution like water, and you put carbon dioxide into it, for example, if you blow into it because you blow out carbon dioxide, the lime water changes from colorless, which it is like water, to like this cloudy white color. That's how you know it's carbon dioxide. So the test is to bubble through lime water. And then you want to say the result is it changes from colorless to cloudy. That's how you know it's carbon dioxide. If it doesn't do that, it's not carbon dioxide. Um, Plankton from SpongeBob. I don't know. Unfortunately, I'm not particularly familiar with SpongeBob, so I can't comment on that. Um, 5B, is that it? Is that it? 5B equal to 3. Right. So yes, in answer to your that's it, I suppose, in what people have asked me. But in answer to your question regarding the science, what you need to do is find out what science topics you need help with. Tell us beforehand. We can then send you some questions on that to help you at home. If we can do it in the lesson, fine, but we have a bit of a structure that we follow. We can't always do specifically what you want because there's other people in your group that might not need that, but we are doing some physics, and if it overlaps with what you need for your test, then obviously we can do some of it. But otherwise, you should still send us tell us what you need help with beforehand, and then we can send you some questions on it to practice. You can, but I'd recommend you send us a message on the WhatsApp with the topic list rather than just ask in the lesson, because I can't guarantee he'll be able to help you in the lesson. Can't you use the practical where you put a beaker on a candle for the carbon dioxide question? Interesting. Interesting. Um, are you trying to say that the candle then goes out because it's carbon dioxide? I think that's what you're talking about, aren't you? Um, I wouldn't risk it. So, let me just see what I'm looking at. So S3, 5B. Yeah, it says specifically the thing that I said about the lime water. Um, so whilst I know what you mean, which is that if you put a candle, um, put a beaker on a candle. Well, okay, no, you can't. I'll tell you why you can't. Because if you have a candle, here's my illustration of a candle. Okay, and you put a beaker on top of it. Are you saying that because the candle goes out, that proves that there's carbon dioxide? Is that what you're saying? Um, because if you are saying that, then that doesn't work because the reason the candle goes out is not because of carbon dioxide in that situation. It is because there is no oxygen. It's a slightly different point. The candle needs oxygen. What you're doing by putting a beaker on top of it is removing all the air. So the lack of oxygen makes the candle go out. It is not carbon dioxide that is making it go out. It is the lack of oxygen. So it's a slightly different thing. It doesn't prove that it's carbon dioxide. It just proves that there's no oxygen. So it is, I get your point, but it's not white. For the test for carbon dioxide, put lime water, colorless to cloudy. Just, that's what you want to put. Right, okay. On the basis there are no further questions from the Key Stage 3 homeworks, I will have to return. Oh, oh, 5A and B booklet. Oh, we suddenly got more. Okay. I may have done these, but I will do them again because I think there's a lot of repetition across the three booklets here. Booklet 2, 5. Oh, no, it's new. Okay, let's do it. 5A and B. Right, about 3,000 million years ago, carbon dioxide was one of the main gases in the Earth's early atmosphere. Um, about 400 million years ago, plants and trees grew. Okay, coal, we burnt the coal. Okay. The bar chart shows the percentage of some of the elements in this coal. The coal contains 85% carbon. Draw the bar. So you need to draw a bar that goes up to 85. So if 80 is there, 90 must be here, roughly. 85 must be halfway between 80 and 90. So you draw a bar roughly like that. Okay. Coal is burned in the atmosphere to release energy. Two of the products are shown. Right, so when you burn coal, it can produce this stuff called sulfur dioxide. You won't know this yet, but sulfur dioxide is something that can mix with the clouds and produce something called acid rain. And carbon particles are these little bits of carbon that go into the air and they sort of block out the sun a little bit and make it go a little bit darker. And that's called global dimming. Oh, booklet 3. Sorry, I think I've answered booklet 3. 5A and B. So I think I'll just show you the answers because I have answered these now. 5A. Oh, I didn't balance it actually. The balanced equation here requires you to realize that there are 6 plus 4 oxygens on that side, so 10 on that side. To make this 10 as well, you'd have to put a 5 in front of that so that it doubles the 2 to make 10. And the test for carbon dioxide is that we bubble it through lime water and it changes from colorless to cloudy. Lime water is a colorless liquid. If we put carbon dioxide through it, it changes color and becomes cloudy. That's how we know that it's carbon dioxide. Um, when I study a topic for the test and then in the exam they word it different, so I go, yeah, they do. That's what they do, and that's the challenge. They test whether you really understand it, and so you have to you have to understand, and that takes time, so it's okay. 4E, I'm not doing 4E because I've already talked about this several times. The test for alkenes is that thing with the bromine water. I said it's orange. It changes color. We mentioned this in an earlier. I think the same question has been repeated a couple of times. Right, that is that then for you guys. I will return in 10 minutes and I will have a look at what the year 10s had to do with the same topic. And the year 11s had some required practicals to do. So we will do that and I'll be back in 10 minutes. Hello. Does anybody have any questions from the homework? Most of you did chemistry. Some people did do some biology. So if you do that, then I will have that ready as well. Um, but does anybody have any questions from any of the chemistry or biology if you did that? So I have that ready as well. That is from the year 10, isn't it? Organic chemistry. Right. 3A, 1F, 5. Okay, fine. Let me try and do this in order. Um, question 1, F. And then I'll get to try and do it numerically. What does it say? Um, okay, right. In the table above, we've got these alkanes, right? Now, nonane, which is this one here, it says that it will condense lower in the fractionating column during fractional distillation. The other alkanes in the table above explain why. So the fractional distillation column, if that's things there, is hot at the bottom and cooler at the top, which means that as the gases rise, because they've all got different boiling points, remember a boiling point is also a condensing point if we're going the other way. If you're heating up a liquid, it becomes a gas there. But if you're cooling a gas down, it goes back to a liquid at the same temperature, at that same point. So the parts, the fractions that have higher boiling points will condense lower down because it's hotter down there. A gas with a lower boiling point will condense higher up. And now nonane has a much higher boiling point than all of the other ones above it. It's 151 compared to all of the other temperatures above. So you need to explain that it has a higher boiling point. And because it is hotter near the bottom of the column, that's why it says refer to the temperature gradient in the fractionating column. Um, so it condenses lower down where it is hotter. That's it. So it's the things, the bigger things, nonane, decane, these things condense lower down on the fractionating column. Everything else, depending on as it gets smaller, condenses higher up. Um, 3A, don't worry, I'm getting that. Don't worry, don't worry. Right, that's next, isn't it? Three, basically all of three, essentially. Um, okay. Four, right. Polybutene is a polymer made from crude oil in two stages. The first stage is making polybutene. It's to break down large hydrocarbon molecules from crude oil into smaller ones, as shown in the figure below. The products contain two types of hydrocarbons with different general formulae. Name them. Well, you only need to know two different types of hydrocarbon. They are called alkanes and alkenes. They are the two. That is an alkane because of the general formula. That those two are alkenes. The general formula for alkenes is that the hydrogens double from the carbons, whereas the alkane you double and add two. So double 8 and then add 2, you get to 18. The condition in the reactor, right. This question is about something called cracking. Cracking is when you start with a long hydrocarbon and you turn it into shorter ones. The reason you want to do that is because the shorter ones are more useful and they burn better. The process of cracking is basically always the same. You have two things for cracking. You have a high temperature. That's what's going on in here. High temperature and a catalyst. Those two things allow us to crack long hydrocarbons into shorter, more useful ones. Why air must not enter the reactor? Presumably because air contains oxygen, and if oxygen gets in here, then the carbon in here could react with the oxygen and make carbon dioxide, but we don't want that. We're trying to avoid that. So the oxygen in the air could react if it gets in. We don't want that to happen because we're not trying to make carbon dioxide. Suggest a method that can be used to separate butene from the other hydrocarbons. The way we separate all of these hydrocarbons is by using something called fractional distillation. That's that whole column thing that I just explained. Um, and it works because different length hydrocarbons have got different boiling points. Um, yes, oxygen would react, would be fine. Correct. Um, draw butene. Right, if it's an ene, the important thing to remember with any alkenes is that firstly, there's four carbons, but two of the carbons have to have a double bond in the middle, but the others don't. Okay, so there must be one double bond in an alkene. Once you get the four carbons drawn, then you need to put hydrogens around the outside. Just be careful with this because it's easy to go wrong. You need to make sure that every C that you're looking at here has got four lines coming out of it because that represents the four electrons that it can share. So two of them are already used here for that one. So this one has space for two more hydrogens. This one has used two of them here and one of them here, so it's only got space for one more. You can put that at the top or the bottom, it doesn't matter, but there should only be one on that one. This one has used two of them, so it's got space for two more. This one has used one of them, so it's got space for three more. They should all have space for four in total. And then if you count the number of H's here, you will find that I have drawn 8 H's, which is exactly why it is called C4H8. Describe how they form polybutene. Okay, so there is a process called polymerization, which is what alkenes can do. Alkenes have a special ability because of this double bond that it can open up to become a single bond, but then it creates space to join on to something else. And so alkenes are reactive, whereas alkanes are not because of that double bond. So when it says, how do these molecules form polybutene? Poly means lots of. That's why a polygon has lots of sides. So what happens here is that lots of butenes join together. But the way they do that is by opening up that double bond and forming a long chain. So we want to say that many butene molecules um, open up the double bond and form a long chain. That's what polymerization is, and that's why it's called polybutene. Now it's like lots of butene. So we get this long chain of them joined together, but they've only been able to do that because they had a double bond that could join to another one. Um, I'll get to question 5, no problem. Right, that's question 3 done. Right, question 5 has also been asked. Oh, have I not finished question 3? No, I don't. Question 5. Right, first of all, this one, draw lines from these. I'll just do this in order. Hexane is an alkane with 6 carbons. If it's an alkane with 6 carbons, the general formula tells me to double the number of carbons and add 2. So it has to be C6H14, which is there. If it's an alkene with 6, the formula for alkenes just tells you to double the number of carbons to get to the number of hydrogens. So it's that one. And then what would be observed? So the way we check whether we've got an alkane or an alkene, if we actually had it in a test tube, then we add bromine water. And if it's an alkane, there is no color change. It stays orange. Bromine water is orange to begin with. Whereas if it reacts with an alkene, well, it does react with an alkene, and so the orange color changes to colorless. So after this question, I want to do a little quick summary of this. Right. Ethane is an alkane, ethene is an alkene. Compare them. Well, actually, to be honest, I was about to do this anyway. I was about to compare for you alkanes and alkenes, but we're about to do that anyway in this question. So compare the two. So what you should say here is, um, Firstly, I would say, I don't know if this is a mark, but I would say ethane has two carbons joined with six hydrogen atoms, whereas ethene has two carbons with four hydrogens. Sometimes the obvious answer is part of the answer. Okay, that's one thing. Then I would mention that ethene has a double carbon bond, whereas ethane only has a single carbon bond. Just be careful when you're writing this. Make sure you're very clear whether you're writing ethene or ethane. It's very easy to mess that up. Um, okay, that was to be another point. Um, whereas that one has a single, so to say the opposite as well. In terms of their reactions, you want to say that ethene is well, all alkenes are what we call unsaturated. That means that it can react with other substances by opening up that double bond. The double bond can open, become a single bond, and then it can join on to other stuff. So when we talk about its reactions, that's what we mean. Um, whereas ethane can't. You might also, because it's 6 marks, I'm thinking of the different things I could say. You could mention that bromine water test, that with bromine water, ethene would change it from orange to colorless, whereas ethane would stays orange because there's no reaction with ethane. There is a reaction with ethene. Let me see what else we could have said. That's probably all the marks. Oh yeah, don't forget also, when you do a compare question, but I just forgot, so I'm sure you would as well. But when you do a compare question, you can also say what's similar about the things. We naturally talk about the differences, but there are similarities. The similarity here is that both are hydrocarbons. In other words, they are compounds that only contain carbon and hydrogen. You can also say that both have covalent bonds. All of these bonds here are overlapping circles from the covalent bonding topic. We just simplify the diagram by doing it like this. And I think that's it. Yeah, that would be enough for all of the marks there. Um, that was five, six, B, six, seven, eight. I'll just go through it. Okay, so okay, I'll just answer some of these questions while I'm here. That's obviously C2H4, just counting what's below. C3H8 is an alkane, so there's no double bond here. It's just the single bonds. And then you put H's around the outside, and there'll be 8 of them. Done. Um, right. What is the name of this plastic? So when you do this thing called polymerization with an alkene, all you do to name the thing that's formed is put the word poly in front of it. So if it was ethene in here, when I do this thing called polymerization, I just write the word poly in front of it, and that's the name of it. What type of reaction is shown in the diagram? Okay, you wouldn't know this, but it's called addition polymerization. This is a little bit advanced, but it is called addition polymerization. There are a couple of different types, which you will come to if you haven't done already. Um, 7C part 2. So that's the fractional distillation process. I shouldn't need to explain that. That's just always the same. Um, 7C part 2. Name the reaction that releases energy from that's called combustion. Okay, describe how fuel oil is broken into smaller, more useful molecules. This is testing you on cracking. Cracking is when we take a long hydrocarbon and make it into smaller ones. The way we do that is by using a high temperature heat and a catalyst. You don't need to know much any more than that, really. But anything to do with cracking, think high temperature, heat, and a catalyst. But make sure you know what cracking is. It is when we take a long hydrocarbon and make it into smaller ones because the smaller ones are more useful to us, mainly because they burn better than the longer ones. And then there was a question on 8B part 2. That's 8A. Should be fine. B, loads of stuff going on here. Um, Right. Two reasons why, well, I think I just answered this question actually. Two reasons why all the alkanes in the bar chart are better fuels than the alkane with this formula. So all of these are small, short alkanes because it tells you the number of carbon atoms. That's C1H4. That'll be C2H6, C3H8, C5, C6, right? They're quite small relatively. We're comparing these small ones with this one, which is much bigger. There's 30 Cs in that one. So essentially the question is, why are short hydrocarbons better than longer ones? And the answer to that question um, is they are more flammable. The shorter the hydrocarbon is, the better it burns. Then the other thing that you want to say is that the shorter ones also have lower boiling points. Lower boiling points. You can mention that they are less viscous as well. Viscous is a word for thick and gloopy, like comparing custard with water. Water flows easily, custard does not. Long hydrocarbons are like custard. They don't flow as well, which means they're generally just worse to use as fuels because you can't transport them around and so on. Has that answered all the questions? Um, 7A. Okay. The answer to this question, I mean, I really shouldn't need to tell you this because there's absolutely no chance that this is not in your notes. But the diagram to help you to explain how crude oil is separated into fractions, the process of fractional distillation of crude oil, the answer is basically always the same. And what I'm going to do, rather than write it all down, you need to be able to say all of the following. Um, oops. This. Um, so when we do this process of fractional distillation, we have that big, my pen works, that big fractionating column thing. We heat the crude oil that we get out of the ground first until it all evaporates or vaporizes. I think vaporize is a better word. So the whole thing, imagine it's a big cloud of black gas. So the whole thing's evaporated. We put it into this fractionating column. As it rises up, it cools down. Now, because all of the different parts of crude oil have got different boiling points, that means that as they cool down, they will gradually turn back into a liquid, but it will happen at different places because it's hotter down here than it is near the top. So when one of the things reaches its boiling point, it will turn into a liquid and it'll come off here. The rest of it will carry on going. Then another part of it will reach its boiling point. Remember, a boiling point is also a condensing point, which I think is the confusion with this. If you're cooling down a gas, it condenses at the boiling point back into a liquid. So when we get back down to that boiling point, it will condense and we take it off here. And then we take that one off here. And then the rest of it keeps going. We take something else off there because it condenses higher up. Something else condenses higher up. And we have now separated our crude oil into the different parts. So these are the things we want to say. First, we heat it until it all evaporates. As the gas rises up, it cools down. You've got to make it clear that as it's going up, it's getting colder. Because all of the different parts that we're separating have got different boiling points, they will condense at different temperatures and therefore different levels in that column. This question, um, I did this with the students that I taught. This kind of question about describing fractional distillation um, has come up. I mean, I went through about 5 or 6 past GCSE papers, and I think in about 4 of them, quite a lot high percentage. This exact question was there. It was a 4 marks. There's only 3, but it was a 4 marks to just explain those points that I just put there. Um, just basically say that repeat the same thing. So you need to make sure you understand the process of fractional distillation. Make sure you understand that we first heat it all up to a very high temperature. It all evaporates and then we cool it down. It's like the reverse of what you might think. We're not just heating it and letting different things boil. We're letting all of it boil first and then cooling it down because then it turns into a liquid and it's easier to collect the liquid, I think, than collect gases. But that is the answer essentially to that question 7A. Is that all? Do we have any other questions? Because if we don't have any other question, I will probably finish a bit earlier today. Um, yes, it is a liquid at the start. Correct. So it is a liquid at the start, but it's a mixture of different liquids. That's the point. It is a mixture of lots of different things. So the reason why we have to do this is because the mixture of things, it's not useful to us until we separate out all of those bits. And this is how we separate out all of the bits. We heat it all up, turn it all into a gas first, then we condense at different temperatures. So, or we cool it down then. But because they've all got different temperatures at which they turn, but let me try and explain this better. So, imagine this is a temperature scale. All of the in crude oil, there are lots of different things. There are some really short things like C2H6 and some really long things like C30H62. That is a long hydrocarbon, that is a short hydrocarbon. We have lots in between as well. They're all mixed up. Um, we then essentially heat the whole thing up and turn the whole thing into a gas, right? So imagine it's all a gas over here. We then cool it down. Now, all of these different fractions have got different boiling points. Imagine these are the different boiling points. So one's got a really high boiling point, one's got a lower boiling point. The shorter they get, the lower their boiling point gets. As we cool it down, when it reaches this temperature, this fraction turns back into a liquid. Oh, turns back into a liquid. The rest of it doesn't. The rest of it keeps going, cooling down. Then something else turns into a liquid, something else turns into a liquid, something else turns into a liquid. And we're able to then separate them out at different levels in the column. That's what we're doing. Um, the 7B, I assume that's in the year 10 booklet. And then, Ash, you've asked me about how can you tell that each of the fractions is a mixture? Mixtures basically have a range of boiling points. So when you've got a mixture of things, it means that some of them have one boiling point, some of them have a different boiling point. It's not the same. So that's why you know it's a mixture, because there's a range of boiling points here. And how does the number of carbon atoms affect this boiling point? You should be able to answer that by looking at it. Um, okay, fine. Let me move on to the other one. 4C and D and 6D, presumably that's from the year 11. Um, why do we need them all? Because so in firstly, because we use them for different things. I think that's the best answer. We use some of it for petrol in your cars. We use some of it for the fuel that comes out of your stove for fire. We use some of it for plane fuel. They're all slightly different fuels. What fuel is not just one thing. There's lots of different types of fuel, and some of them are used in like bigger vehicles like planes. Some of them are used in smaller things, but crude oil is all of them mixed together. So we're trying to separate them out by doing this process. Hopefully that answers that question. Um, for I'm so confused where I am now. For See. Oh yeah. So I think when you do this, when you do part B of this question, you end up with, if I'm not right, if I've got my memory serves me right, 30 there and 15 there. And the question says the volume of gases collected are in the same ratio as hydrogen atoms to oxygen atoms in a water molecule. Explain how the volumes collected support the hypothesis. Well, in water, what's the ratio of hydrogen to oxygen? There is twice as many hydrogen atoms in water as there are oxygen atoms. What is the volume of gases that we've produced here? What's the ratio? We have produced twice as much hydrogen as oxygen. That's essentially the answer. Um, and then D, yeah, this is an awkward one. There's something wrong with this question, but uncertainty, which you might need for any of the three sciences, is the range divided by two. That's what uncertainty is. The problem in this question is that your range ends up being between two numbers. So your range here is 11 take away 6. Highest take away lowest is 5. 5 divided by 2 is 2.5. Now, that's the uncertainty as far as I'm concerned. But I guess what you do when it's a fraction like that in the middle, you round it up to the nearest whole number. So you end up with that as the answer. And 60. Calculate the gradient of the tangent at 0.4. So you need to find the gradient of this line. Um, 4b, how do you get those values? Oh, sorry, wait, 4b, let me go back. Wasn't it just reading off the tubes? Yeah. So here, this is a 50 centimeters cubed measuring cylinder. The space at the top of the measuring cylinder there, or it's the bottom really, it's upside down. But that space there, here, is the amount of oxygen, and this is the amount of hydrogen. So what you have to do here is sort of read the measuring cylinder upside down. If you're reading this upside down, it's a 50 centimeters cubed measuring cylinder. So it must be, that must be 10. Wait, was that right? Yeah, 10, 20, 30, 40, 50. Okay, so if that's 10, 20, 30, 40, 50, then that much is 15. Similarly, this, for the same reason, is 30. That's how I got those numbers. Um, and 6D asks you to, when you're doing these questions on rates of a reaction, you will often have to calculate the rate of a chemical reaction at a specific point on the graph. The only way you do that is by drawing a tangent. They've already done the tangent for you. What you then have to do is find the gradient of that tangent. Now, the way you find the gradient is now maths, basically, is you make, what I would do is make a little, hard to see, triangle. Okay. Um, Count how many up and down you've gone and count how many across you've gone, and then you do up divided by across. That's how you find the gradient of a line. In this case, it's down, but so this is at about 15. I don't think you need to be too precise with this. Um, that's about 5, so that means it's gone down by 10. Um, and then it's gone across from 0.1 to 0.6, roughly, which is 0.5. If you do the up divided by the across, it would be 10 divided by 0.5, um, or minus 10 divided by 0.5, which is minus 20. That is the gradient of the line. The unit then, and you get this a lot across all of the sciences, where you have to state a unit from a graph. If you found a gradient of a line, the way you did it was by going across, sorry, up divided by across. All you do for the units now is take the same units from the axes. So the up and down units were seconds divided by the across units, which were moles per dm cubed, which is a bit of a weird way of presenting it, but that would be fine. Um, but that's what you do. So you don't have to really understand it. But if you are finding the gradient from a graph, you are taking the up divided by across, which is why if we just link this to a different topic, on a distance time graph, the gradient of the line tells you how fast you're going. Now, if the distance is in meters and time is in seconds, that gradient or the speed is in meters per second because it's meters per second from the scale. SDM cubes per mole, yes, you can, because you're doing that divided by dm. Yes, you can. Seconds dm cubed per mole is absolutely fine because it's the same thing. If I do that divided by moles per dm cubed from maths, you times and flip over, so it's seconds dm cubed per mole, which is the same thing. Yes, that's probably the better answers, to be honest. Right, is that everything? Are we satisfied? I believe next time you are just, I think for year 11s, I think we're just on to major revision stuff. And even for year 10, we're just basically going back to earlier topics and doing exam questions and stuff in the lessons. With the exception of a couple of maths topics, I think we're still doing a couple of maths things, but the sciences is basically just free for all revision, essentially, ahead of any exams that you might have at the end of the year. Right, on the basis that there are no further questions, I will end today. If you do have any further questions, then obviously you can message us, and I will do my best to assist whenever possible. Right, I think that's it. I'll see you later.